Hello and welcome to section 1.6. Today we're going to look at solving linear inequalities. As we look at linear inequalities, we're going to look at two different types. The first one is going to be simple inequalities. Then we're going to go ahead and take a look at compound inequalities. And if you think back to Algebra 1, hopefully you remember that inequalities have properties that are very similar to those of an equation. Now, an actual inequality, and I know we've discussed this before, is going to be something like less than, greater than, less than or equal to, and greater than or equal to. So these right here are what we're going to be dealing with in lieu of the actual equal sign, which is what we'd be dealing with in an equation. And I wanted you to remember that when we're talking about a solution, remember a solution is the value of a variable that makes the inequality true. And this piece right here is key to having a solution, is it must make it true. In a few sections ago, we talked about transformations that would produce equivalent equations. Well, if you open your book up to page 41, now we're going to look at transformations that are going to produce equivalent inequalities. And these are actually, they're very, very similar with the exception of the last few, and we'll go over those here in a minute. Now, as we discussed before, if we want to produce equivalent inequalities, we can add the same number to both sides. We can also subtract the same number from both sides. We can multiply both sides by the same positive number, or we can divide both sides by the same positive numbers. Now the differences are going to come here in these last two. When we multiply both sides of an inequality by the same negative number, the key thing that we're going to have to remember to do is we're going to have to reverse the inequality. So that means that if we're going to multiply an inequality by, let's say, -1 on both sides, and I was dealing with a greater than symbol, I'm then going to take that greater than symbol and reverse it to read less than. Okay, and the same thing is going to happen when I come down here and I divide both sides by the same negative number. Because it's a negative number, we're again going to have to reverse the inequality that we are originally given. And we'll do that here in the next few examples. When we go to graph an inequality, the graph of an inequality is going to consist of all the points that are going to fall on a real number line and that are solutions to that inequality. So when we graph an inequality, we are going to use an open circle over the point for the inequalities that are either less than or greater than. And then if you remember from Algebra 1, if our inequalities are a less than or equal to or greater than or equal to, then we're going to use a closed circle over that point. So based on the information we've been given, let's go ahead and start some examples. Example 1 says that we want to solve 11y minus 9 is greater than 13. Now because inequalities are like an equation, we're going to treat this just like an equation, and we're going to just go ahead and solve for y or try to isolate that y variable. So in doing so, I'm going to start out by adding 9 to both sides, and this is going to give me 11y is greater than 22. I then want to go ahead and get y by itself, so I'm going to divide both sides by a positive 11, and I end up with y is greater than 2. This right here will then become my solution. And when I graph this, I'm going to graph this over here on the number line. So I'll just go ahead and list a few points here. We have -2 and -4. Now because of my inequality right here, because this is a greater than symbol, when I go to graph this, I'm going to put the closed or I'm sorry, the open circle, because I do not include 2, I'm going to put an open circle over 2, and I'm going to pick a test point, and I'm going to essentially shade or draw an arrow in the direction where my inequality is true. So if I go ahead and pick the test point of 0, and I plug 0 in for y, is 0 greater than 2? The answer would be no. And because 0 lies on the left side, and it's not a solution, that tells me I'm going to have to draw my arrow to the right. So if I go ahead and come in here, all my solutions should then fall in this direction. And if we pick a test point just to verify, let's pick 4. Is 4 greater than 2? And the answer would be yes. So this confirms my graph. Now for some of you that are doing your graphs on paper that either have like the black number line and you don't have a colored pencil, or you're doing it with pencil or pen when you're doing your homework, if you want, above the number line, you may go ahead and come up here and draw an open circle above 2, and then draw an arrow in this direction, just to make it a little bit easier to see. We're going to do something very similar in example 2. Example 2 says to solve 7x plus 9 is greater than or equal to 10x minus 12. And again, just like with an equation, we're going to want to get all of the x values on one side, all the constants on the other, and then solve for that variable. So if I go ahead and I subtract 7x from both sides, this is going to give me 9 is greater than or equal to 3x minus 12. Then I want to get the constants all over onto the left, so I'm going to add 12 to both sides. And when I simplify this, I end up with 21 is greater than or equal to 3x. I'm going to divide both sides by 3, and we're going to figure out then that 7 is greater than or equal to x. Now I can also rewrite this as x is less than or equal to 7. Either way, you produce equivalent inequalities. Now when I go to graph this, I have to have values that are less than 7. And to be less than 7, then that means that they're going to be smaller. So if I draw my number line, I have 0, 2, 4, 6, and this here will actually be 7 on the end. Then we have negative 2. I'm going to go and I'm going to put a closed circle on 7 because of the less than or equal to symbol. So if I come up here at 7, and I'm going to fill in that circle, and my values have to be less than 7, which then tells me that I'm going to be drawing my arrow to the left, then this is the graph of my inequality. If you have questions on these examples, please write your questions down, and then I'll answer your questions when I return to class. Next, we have example 3. Example 3 is a story problem, and it says the percent of households H with cable TV can be modeled by the formula H equals 2.3y plus 44, and we're given that y is the number of years since 1998. We want to describe the years when the percent is less than 53.2. So we've just completed reading the problem. Now I need to assess the information that was given. I see that I'm given an equation. I know that H is going to be the households with cable TV. Y is the number of years since 1998. And we're looking for the percent that is less than 53.2. Now in this case, for the modeling portion, I'm given the model that I'm going to be using. We're given that H is equal to 2.3y plus 44. So I don't have to essentially come up with a model, but I am going to have to know that I want to describe the years when the percent is less than 53.2. So what that tells me then is I'm going to take this equation and I'm going to set it less than 53.2. So essentially what we have is 2.3y plus 44 is less than 53.2. Now I have my equation and I can then go ahead and solve. So to solve, I'm going to go ahead and subtract 44 from both sides. And we're left with 2.3y is going to be less than 9.8. And if I divide both sides by 2.3, you'll see that we end up with y is less than 4. Okay, so here is my algebraic solution. Now I have to put a meaning behind that. So because my original problem stated that it wanted us to describe the years when the percent is less than 53.2, and we know that y is the number of years since 1998, and I came up with a solution of y is less than 4, what that tells me then is if I add 4 years to 1998, I end up with the year 2002. So I'm looking at the years before 2002 is when the percentage will be less than 53.2. The last thing we're going to look at are going to be compound inequalities. Now, compound inequalities means that we have two inequalities that are going to be joined with either the word and or the word or. And to look at an example, if I give you something like -2 is less than or equal to x, which is less than 1, this here would be considered an and problem. And if I gave you an example that said x is less than -1 or x is greater than or equal to 2, this then would be an example of an or problem. Now to graphically show this, what I would have to do is I'm going to come over here and I'm going to put in a 0, 2, 4, and 6, and we'll do the same thing over on this side. Now to graph something like this, I'm essentially looking at values that are going to be between -2 and 1. And because of this less than or equal to symbol, I'm going to come over here to -2 and I'm going to put a closed circle on -2. And because of the less than symbol before the 1, I'm going to come over here to 1 and I'm going to put an open circle. And then I'm looking at the values that are between -2 and 1. So when I graph this, I'm going to connect those two circles with a solid line in between. So my solutions then are going to be any number that falls in between -2 and 1. Likewise, on the other side here, I have 0, 2, and 4, and then -2, -4. To plot the point for values of x that are less than -1, I'm going to come over here and I'm going to put an open circle on -1 because of the less than inequality symbol. And when I'm looking at values of x that are less than -1, that tells me that I'm going to the left. So I'm going to want to show that my arrow is going in this direction. And then I'm also going to go and put a closed circle at x equals 2. And I'm going to plot the solution points for when x is greater than 2, which is going to give me all of the numbers or points to the right. So this is how I'd graph an OR situation. So let's look at example 4. Example 4 says to solve the compound inequality -9 is less than t plus 4, which is less than 10. When doing compound inequalities, our goal is going to be to isolate the variable between the two numbers. So in other words, if I have -9 is less than t plus 4, which is less than 10, I'm going to try to isolate this variable t, and to do that, I need to get rid of the positive 4. So to undo a positive 4, I'm going to subtract 4 out of the middle, and if I subtract 4 out of the middle, then I must also do it on the left and on the right. So when I go to simplify, I end up with -9 minus 4, which is going to give me a -13, which is going to be less than. These 4's are going to cancel, which is just going to leave me with t. And then I have that is going to be less than 10 minus 4, which is 6. So my compound inequality then is -13 is less than t, which is less than 6. Or I'm looking for solutions that are in between -13 and a positive 6. So if I go to graph something like this, and I have a -13 here, I have a 6 here, I would put an open circle on -13 and on 6 because of the less than inequalities, and I would shade everything in between -13 and 6, just like that. And last but not least is example 5. Now example 5 tells us that we're going to solve 6x plus 9 is less than 3, or 3x minus 8 is greater than 13. So what I essentially have here is two different inequalities, and I'm going to solve them like an equation, so I'm going to have to solve them independently of one another. So if we start out with this 6x plus 9 is less than 3, I want to isolate my x value, so I'm going to do that by subtracting 9 from both sides, which gives us 6x is less than -6. Then I want to isolate or get rid of the 6 that's attached to the x, so I'm going to do that by dividing, and I'm left with x is less than -1. So there's one aspect. Then I'm going to come over to the other side, and I'm going to simplify. The 3x minus 8 is greater than 13. I want to get the x by itself, so I'm going to add 8 to both sides, and I end up with 3x is going to be greater than 21. We're going to divide both sides by 3, and we're left with x is greater than 7. So this would be my second solution. And then I want to just verify that I've done everything correctly. If I have an or situation, does it make sense that x is going to be less than -1 and greater than 7? And because I can have values that are greater than 7 or less than -1, then this is going to work. So I have now completed example 5, which is the last example in section 1.6. Again, if you have any questions, please be sure to write them down, and I will answer them as soon as I return. On that note, I hope you guys have a great day, and I will see you later. Thank you.